Thanks for introducing myself. I'm Xiaochen, a PhD student from Peking University. In this presentation, I will introduce our work on a domain-specific accelerator for solving partial differential equations, which leverages a Dataflow architecture to achieve high efficiency for a key computation, a sparse triangular solver. Partial differential equations finds numerous applications, ranging from describing particle motion to seismic wave propagation, and from electronic design to aerodynamics. Therefore, PDEs are fundamental, and accelerating their solutions plays a crucial role in enhancing the efficiency of HPC applications. PDE is an equation that involves an unknown function of multiple variables and its partial derivatives with respect to those variables. Here I show a typical Laplace equation. Solving it through a numerical method typically requires discretizing the entire problem space and calculating the function values at its discretized point. This method usually employs a standard pattern where each point is calculated based on its neighboring values. Specifically, a finite difference method approximates derivatives with differences between function values, converting the original PDE into a linear equation that involves 7 variables. The coefficients of each point's linear equation are stored in a matrix, forming the system AX equals B. The matrix A represents the connections between grid points and thus exhibits a structural sparsity pattern that follows the standard. Solving the system AX equals B is challenging for large-scale systems. Iterative solvers are commonly used, starting with an initial guess and refining it until the solution meets the desired accuracy. We classify the existing iterative solver accelerators based on 2 factors: solver complexity, names basic versus advanced, and applicability, PD specific versus general linear systems. Our work is the first to focus on advanced solvers for PDEs. Coverage region's speed is a critical factor. The advanced solvers used by Telos achieves tens of times faster than the basic method employed by the previous work, but it comes with increased complexity. Accelerating iterative solvers remains a significant challenge. HPCG is a common benchmark used to rank supercomputers. In the latest results, most systems achieve less than 1% of their peak performance, highlighting the limitations of the state-of-the-art software optimizations for general-purpose systems and emphasizing the substantial room for improvement through architectural specialization. We focus on the conjugate gradient solver with an incomplete Cholinsky preconditioner. Preconditioner is a technique used alongside the iterative solvers to accelerate their coverages. The incomplete Cholinsky method factorizes the coefficient matrix A into a lower triangular matrix and its transpose. Their product approximates A, but is not exact, which is very incomplete. The factorization is performed only once, while the sparse triangular systems are solved at every iteration. We also profile the execution time of the solver, which consists of kernels such as SPMV, vector operations like dot products, and SPTRCV. We observe that SPTRC accounts for nearly 80% of the solving time, presenting a significant performance bottleneck. It has unique traits that cause low efficiency and needs further study. SPTRZ performs the forward substitution process, solving variables iteratively by starting with the first equation and substituting the solved values into subsequent equations. This process introduces a loop carry dependency on computing a partial sum and to solve the values. Here, we illustrate this using an example. The matrix is derived from a 7-point central pattern and is a triangular matrix generated by the preconditioner. The first variable is solved directly, and its value is then propagated to the rows corresponding to x1, x2, and x4 to compute the partial sums and solve them. We can find these variables depend on x only. A dependency graph is accordingly built, where each node represents a variable and the edges indicate the dependencies between variables. Following this process, all variables are solved iteratively and a complete dependency graph is built. Nodes of the same colors are independent. The dependency graph can be divided into multiple levels, with each level containing independent variables. Thus, optimizing SPTRSV is difficult because the achievable parallelism is determined by the distribution of non-zero elements. We observe that GPUs faces fundamental limitations in effectively accelerating SPTRSV. First, GPUs are specifically designed for massive data parallel workloads, and their synchronization mechanisms are cost-grand and expensive. Organizing SPTRSV computations into threads requires synchronizations within thread blocks using barriers and across thread blocks using span weight mechanisms. These frequent synchronizations result in excessive stores to manage widespread dependencies inherited in SPTRSV. Next, GPU must communicate dependent values through the memory hierarchy. This high communication overhead forces the threads to wait for their values to be communicated, leaving a large portion of warp stored. As GPUs relies on the warp scheduling to hide access latency, this overhead leads to an insufficient number of eligible warps for scheduling and results in low memory bandwidth utilization. In contrast, Dataflow accelerators present a promising solution to overcome the limitations of GPUs. First, Dataflow accelerators get rid of explicit synchronization mechanisms, thereby minimizing the overhead. As mentioned, SPTRSV naturally follows the dependency graph of variables, with P's triggered by the data availability, enabling a fine-grained asynchronous execution. Second, Dataflow accelerators are typically organized in a spatial structure, where P's directly communicate with its neighbors. This results in a fixed and minimized latency for resolving dependencies, allowing communication and computation to be effectively overlapped. Consequently, utilization improves as P's keep busy with eligible computations, avoiding stalls commonly observed in GPUs. While Dataflow accelerators demonstrate significant advantages, designing an efficient architecture remains a challenging task. Our goal is to exploit the structural sparsity patterns inherent in PD solvings to accelerate SPTRSV kernel. Different equations employ diverse numerical schemes, resulting in sparse matrices with distinct dependency patterns, which pose challenges for architectural support. We propose a Dataflow design framework that includes a pipelining technique to organize computations into wavefronts and efficiently map them onto Ps. In addition, we introduce a communication aggregation technique to optimize communication by combining the product terms of the same target. Building on the Dataflow design, we propose an architecture featuring specialized compute units that support flexible configurations for different patterns. Next, we will focus on the technical details. Our pipelining technique is based on partitioning computations into subsequential stages called wavefronts. For example, in a central pattern, 3 points depend on the central point, and these points are independent and form a hyperplane satisfying I plus j plus k equals 1. Our mapping strategy assigns each hyperplane to PEs and schedules them sequentially to maintain dependencies. However, this method fails for complex stantial patterns. In this example, some points fall into hyperplane 1, 2, 3, and they are working as expected. But some points fall into the hyperplane 0 and minus 1, which are executed simultaneously with or even prior to the central point. The dependency order cannot be preserved. We refer to this as the backward dependency, as they point relatively to the hyperplane execution direction. We propose a Wang transformation to resolve the backward dependencies. In this example, 3 points are identified as backward dependencies. Our approach first focuses on the YZ plane and then rotates the y-axis towards this point. As a result, points are assigned new coordinates in the x, y prime, z system, and backward dependencies still exist in the negative z direction. We then rotate the x-axis towards the outermost point. In the new x prime, y prime, these coordinate systems, all backward dependencies are removed. After the Wang transformation, grid points are assigned to P's based on their x and y coordinates, and points along the z-axis are processed sequentially. Hyperplanes ensure computations are executed in the dependency order. For each variable, the dependent variables or product terms must be gathered from other P's. It's then scattered to other P's for further computations. These variables reside in different P's at different time steps, leading to a high communication and computation overhead. We propose a communication aggregation technique to combine product terms of the same partial sum as they transfer between P's. Blue points with a distance of 1 are called group 1, representing variables mapped to the same P and its neighbors. The 2 blue points also need to resolve their dependencies, and they have their own set of group 1 as yellow points. The 2 yellow points also serve as the group 2 for the origin point, allowing us to combine them into a partial sum during their transfer between P's. Similarly, the yellow points also contribute to the green point. And this green point serves as the group 2 and group 3 for other points, resulting in a communication path from the lower left to the upper right corner. This approach reduces the communication volume and distributes computations across multiple P's, significantly improving the efficiency. Our architecture is built upon the proposed data flow design. The P array is responsible for a cube subdomain of the grid space. Some points outside of the domain also fall into the stantial. They are called halos, and we have a specialized unit to handle them. For memories, the vector buffers store the variables and the right-hand side, while the matrix buffer stores the coefficients. Finally, our architecture supports multiple patterns with the controller reading the corresponding configurations. Our P architecture is specialized for the computations within SPTRSV. First, a scalar unit is responsible for solving variables using values from the buffers or the neighboring P's. Next, a vector unit computes multiple product terms in parallel. The vector lengths are partitioned to interleave the product terms from different variables, and they are reused in a FIFO manner. The latest variable is multiplied with its group 1, and the earliest variable is multiplied with its group 3. The next component is an aggregator that combines the partial sums and forwards the results to the corresponding ports. The aggregator supports a primitive that defines the vector length and the input ports to be combined and the destination port. This functionality is essential for supporting diverse patterns. We evaluate SPTRC latency using matrices generated from common central patterns used for solving PDEs. Telos achieves an average 8 times speed up over a GPU. We explain this using the ratio to the roofline peak throughput. GPU performs better with larger matrices. By leveraging their numerous independent warps to hide access latency. But these improvements are limited by resources constraints. In contrast, Telos consistently outperforms them across all sizes by optimizing both parallelism and dependency resolution. We also conduct experiments on the complete PDE solving process. Compared to existing accelerators, we achieve significant speed ups despite the higher computational complexity per iteration. These results highlight the generality of Telos for advanced solvers. In conclusion, we propose an efficient data flow accelerator that leverages the structural sparsity patterns. It is specifically designed for SPTRSV in PDE solving, a task that challenges general purpose processors but is well suited for accelerators. Thank you.